All right, welcome back to CS267. And I'm going to talk today about data parallel algorithms, which in this lecture is sort of inspired by GPUs, although these data parallel algorithms can also be used on a lot of other types of hardware, but it's something that will come up and hopefully you'll see why as we go through the ideas and what a data parallel machine, an abstract data parallel machine looks like. So just to remind you, we talked earlier at the beginning of the semester about different types of parallel machines. You're now getting some familiarity with shared memory machines. And next week, Aiden will be talking about distributed memory machines, which are in the middle here. And you've heard about them a little bit in some of Jim's lectures as well. And today, I'm really going to focus on this idea of a single instruction multiple data machine, which is really the underlying machine abstraction for data parallel algorithms. So the idea here is that we have a single processor, and it broadcasts out instructions to all of the other processors that are doing all the computational work, and they can also share memory as in, say, an SMP. And so hopefully that looks a little bit reminiscent of the GPU architecture that I showed, that what an SM node, for example, a streaming multiprocessor looks like inside of a GPU. Whoops. And let's see if we can get back to the right page here. So why are we're going to look at this idea of how to organize algorithms around the idea of data parallelism, which performs the same operation on multiple values, often array elements. People tend to use the term somewhat loosely, data parallelism, anytime you're doing a bunch of independent things on different data values. I'm going to think about it today in a more sort of pure data parallel way, where each instruction is really executing together across a single instruction is executing across on our abstract machine, all the processors at once in a single step. So they're really working in lockstep in this sort of abstract machine model. A lot of the ideas that you'll see here come up not only in programming GPUs and something like CUDA, but also will come up in algorithms that you're trying to map onto the SIMD units, or previously, and I'll say a little bit more about this, SIMD supercomputers, algorithms that are being implemented inside of MapReduce, or at least the reduce operation, and the MPI collectives, which will come up when Aiden talks about message passing next week. So it's really about these kinds of algorithms, and you've seen a little bit of, we've seen reductions also in OpenMP. It'll come up when we talk about these kinds of things that use things like broadcast and scan for communicating between the processors, as opposed to just asynchronously reading and writing shared variables. So I'm going to introduce some the basic underlying primitives in a data parallel model. The first one and the easiest one is unary operators that can be applied across an array of elements. So for example, if we have an array A and an array B, and we say B is equal to f of A, where f is a unary function such as the square function, then it's just going to square every element independently. And you can see how this would map easily onto a GPU or lots of other parallel hardware for that matter. Similarly, a binary operation such as addition, or in this case subtraction, can be applied element-wise to all the elements of two arrays in this case. And so we just have arrays A and B and take the difference between them, and that is in the result C. And we might have some notation like this. This kind of array notation, you might see it in MATLAB with some variations. You might see it in, if you're familiar with some of the languages like APL, but a lot of other places where we'll see this kind of array notation that comes up. And I'll sort of introduce it along the way without giving you a formal language definition for it. And now the next thing you might want to do is you might want to broadcast. As I said earlier, the broadcast and reduction are some of the primitives that really come up in data parallel programming. So we can write something as simple as just saying that some array B is equal to some scalar value A, and that will cause it to be broadcast. And so the notation might look something like this, with just B equal to A. And of course, this is used for things like SAXB or DAXB operations that are doing AX plus Y. You just do the multiplication by the scalar and across all the elements of the X vector, and then add them pairwise or element-wise to the elements of the Y vector. Now, memory operations here, and this is one of the places where SIMD hardware, the SIMD hardware that you've seen on CPUs, hasn't always provided some of the same power that data parallel, some of the other data parallel sort of hardware have provided. But in any case, for a lot of these algorithms to work, we really want to be able to access non-contiguous memory in various ways. So we can have just a simple contiguous memory operation, which at the programming language level might look something like A is equal to B, where A and B are both arrays of the same shape, or at least let's say that they have some intersection in their index spaces, and that will write the elements of B onto the elements of A wherever there's an intersection. And you might have you can do an assignment statement that has a stride. So you can access an array in general that has with a stride. So here we're saying that the array B we're going to copy the elements between inclusively 0 and 4, but with a stride of 2. So every other element. And so if we, so we can have a smaller array, for example, that we're writing onto. And we can also use this sort of MATLAB-like notation to say, excuse me, we want to a particular column or a row of an array. Excuse me. So we can also then do gather or scatter operations. A gather operation or indexed operation means we're going to use a separate array as an array of indices and use that using the array notation. So on the right-hand side here, we're doing a gather of the B matrix by passing in not just a single index into B, get one element out, but to get out a set of elements in a particular order that's given by this index array X. And so you could see then if we've indexed B by that, which has just the numbers 0 through 4 in order, but then we do an assignment statement or we read from it, we gather from it in the order given by these indices, and the first element is going to be whatever is stored at position 3, which is the 3.3, and so on. And the opposite of that is the scatter operation, where we put the index array on the left-hand side, and we're saying A indexed by the X, or the index vector is going to be written, we're going to get the elements of B. So B is now in order, but the question is, which element of A are we going to be writing into? And that's determined by the X vector. Now, when we put it on the left-hand side like this, there's some questions that come up. Most obviously, what if we have something that's not a permutation in an index array, but actually has repeated values? So an extreme case here is where X actually has just the value 0 in it. We then have to have either some rules that say which one of the values is going to end up as the final value inside of here, or perhaps the language will just say that this is not well defined, that you'll get any one of the values. Hopefully you'll get one of the values that was at the position in the B matrix here, or B array, that you're not going to get some scrambled set of bits by simultaneously writing into them, which wouldn't generally happen on any modern hardware. Now, the other thing that comes up in data parallelism is the idea that as we're performing these array operations, and we saw a little bit of this on Tuesday talking about GPUs, that we're going to want to mask some of the processors, the logical processors that are associated with each of one of the array elements. So maybe I should have said that to begin with. We can think of each one of these elements as having a processor sitting at it, and so we can do computation sort of right there at any one of the array elements. But we sometimes want to turn some of those processors off because, for example, there's some conditional part of the code, and rather than writing code with conditionals, which we will do when we're working on GPUs, we may want to instead think of this as having a mask. So it's really clear to us what's happening, which is, for example, we're adding A and B together, but B is being masked. And so we're only picking up certain elements of B before we're doing the addition. And now a reduction operation, we saw a broadcast earlier, but we haven't really looked at a reduction. A reduction, of course, is sort of the inverse of that. It's taking an array and producing some value using an associative operator of some kind, an associative binary operator, in this case, an add operator. And it's associative so that the parallel hardware can perform these operations in any order and still get the same answer. And sometimes we will be a little bit loose about this, for example, with floating point arithmetic. arithmetic, and we'll still use these kinds of, we'll treat these operations like addition and multiplication as associative and floating point, even though technically you will get a different answer. And you have to be a little careful about how that gets used in various algorithms. But that at a higher level, we're going to use this to for example, add up all of the elements of the array. And we can do things like dot products, where we're computing, say, the dot product of X and Y. And that gives us these, the sum of the products of the pairwise elements of X and Y. Now we can also, there's also a primitive, and this is perhaps the most important primitive today in this lecture, because you've seen versions of the others before, and they're all pretty straightforward. This one is a little bit different in that a parallel prefix is going to be like a reduction, but leaving every partial sum. For example, if we're doing addition, a reduction with addition, or in this case, a scan with addition, we're going to leave each partial result in every element of the array. So if we've got this array A with the values that are shown here, 3, 1, 1, etc., and we do a sum scan on that, and this is as written here, this is what we call an inclusive sum scan. So the first element is just the sum of the first element, which is just the 3, and the second one is the sum of 1 and 2, and so on. And we can use this for max operations. So anything that, again, is an associative operator, it can be useful to do various kinds of scans that'll come up in these data parallel algorithms. And this is probably going to be the most interesting primitive for building algorithms of things that are fairly non-obvious in terms of their parallelism. They'll almost always have a scan operation in them. There are both inclusive and exclusive versions of these. I won't read through the notation here, but again, this little circle is just indicated that it can be done on an arbitrary set of operators as long as they're associative. And the inclusive scan then includes each one of the elements at that position when, say, adding up all the elements to the left, whereas the exclusive one only adds up the elements to the left, but doesn't include the one at this position as as the output. And we can easily go back and forth between the two. So there's some algorithms that are going to be easier to write with a exclusive versus inclusive add or scan, or vice versa. And it's easy to get the inclusive value out of the exclusive value, even using the primitives I've talked about so far. Namely, you can just add the input array X onto the result of the exclusive scan, and that'll give you the inclusive scan. Now, if you want to get the the exclusive one out of the inclusive one, that was a little bit harder. You either need to have an inverse operation. So for example, with addition, we would use subtraction. So we'd subtract off X and get the exclusive array result out of that. Or if you have some operation that doesn't really have a max, then, doesn't have an inverse, then you would need to use some kind of a shift operation. And shift operations are often used in these data parallel languages as well. They of course require communication, and we'll see if we've got a processor sitting at every element. But we'll need communication for some of these other operations as well, such as broadcast and reductions and scans. So I'm now going to just talk about sort of idealized hardware and a performance model. I'll just check to make sure there are no questions. It doesn't seem like anything has come up yet. I think most of this is pretty straightforward so far. So in our SIMD machine, we're going to have a large number of usually very simple or tiny processors. And so the single processor is called the control processor. And you can think of it as broadcasting the instructions out to each of the individual processors that are doing the computation. They each have some memories associated with them, although they may also have the ability to directly read and write somehow through this interconnect network through to the memories of the other processors and so on. And the cost model is that we're going to just assume we have an unbounded number of processors, that the control overhead is free, and that the communication is free. So none of these things, of course, are realistic assumptions, but it is a nice way of designing algorithms that will give us good complexity analysis. And this abstract machine model will give us what we call the scan, or the depth of the algorithm, based on how many steps it has to take on a machine that has this sort of free communication and unbounded number of processors. So what happens when you run on an infinite number of processors? So going back to the primitives, what's the cost of each of these primitives? Well, something like a unary or binary operation, which are sometimes called embarrassingly parallel, or here a more positive version of it, pleasingly parallel, is a constant time operation. So independent of the size of your arrays, A, B, and C, you can do this in constant time on our idealized hardware because it's got an infinite number of processors. And even if the arrays are not aligned, the communication here is free. So we don't really worry about the fact that we may be doing shifts or something like that in order to get the arrays lined up. But that it does become an issue in practice when we map it onto real hardware. What about a broadcast and reduction? Well, we can do something, either one of these in a logarithmic number of steps in the size of the array using a tree of processors that has depth log n. So just to be really clear about this, here's our broadcast of one value on P processors. There's our broadcast network, and there's our reduction network. And this just shows you the log n span of this algorithm, both of these algorithms. And they take, in the reduction, of course, it's taking advantage of associativity, because if you were running this serially, you would add up, say, the 1 and 3, and then the 1, and then the 0. And whereas in this case, you're going to add up I guess 3 and 2 here before you add up the other elements, or at the same time as you're adding up 1 and 3. So you might ask the question, can we do any better on a parallel machine? So this was an algorithm that I gave you a high-level picture of for doing a broadcast or reduction. And by the way, people use other tree shapes for these things, but you typically will use a logarithmic algorithm, at least once you get to a certain scale of machine. And on small enough machines, you may use something else that's more like a linear time algorithm. But in any case, you might ask, on our idealized machine, can we do anything faster than this log n time for doing something like a reduction? And the answer is no, that there's actually a lower bound that says that you can't do this in time that is faster than log n, in fewer than log n steps. So what is the idea of this argument is that we're going to take our n useful input values, and at any particular time, what do I mean by useful? I'm saying that I'm trying to figure out how many steps does it take to do any operation at all on n input values. And we have to be doing something useful with the input values. So with the input values, we can't sort of just make them up as we're, as throw in extra input values. We're trying to figure out how we can compute on the actual things that we want to do reduction on. And so after one step, we could have one output here, which is just the output of 2 of the input values. Now we can do a bunch of those in parallel. We've got an unbounded number of processors, and that's fine. But in terms of the output, given that if we have only binary functions in our that we're building this computation out of, then after one step, the output, which comes out of one of those binary functions, can only depend on 2 of the inputs. And similarly, even if we had, say, ternary operators, as long as we've got operators with finite branching factor, we can only have we can only have something like, binary or ternary or whatever, a set, or 3 inputs or 2 inputs that we can depend on. And so now as we go up by induction, then we can see that after k time steps, we can only depend on 2 to the k inputs. And so this binary tree actually performs this computation. So this just shows that there's also a lower bound that says it's going to take log n time, if we're building out a binary operation, then log base 2 of n time in order to do any computation on n inputs. All right, let's look at something a little bit more interesting. So you've looked at matrix multiply in homework 1. Let's look at a parallel version of this. And Jim has also talked about this and looking at in his lectures last week. But just to think about this in this context of our data parallel machine, what is our algorithm for multiplying n by n matrices? Well, we can actually multiply n by n matrices. So each of these matrices, of course, has n squared elements in log n time. So how do we do that? Well, we're going to use n cubed processors, so a lot of processors, and we'll put a processor at every one of the grid points inside of this cube. And this cube has, let's say that's an n, these are n by n matrices, it's going to be an n by n cube, and each one of the loop indices, if we were thinking about the 3-nested loop version of matrix multiply, we have the I and the j loop, and those iterate over the C matrix, which is here on the top. and then say the I and the K loop, which iterates over the A matrix and so on. And so at every one of those positions in the middle, we're going to put a processor in the interior of this cube. And that processor, in using those n cubed processors now in a single time step, so in constant time, we can multiply each of the AIK and BKJ elements, so one element from A and one element from B, in order to get some value that's going to be sitting there as a temporary, which we're calling PIJK, sitting in the middle of this cube. And the second step then is we have to do a reduction on all of the pencils, the vertical pencils, in order to get the output value C. And that can be done in log n time, because using n squared of these trees. So you still need a bunch of processors there in each one of the columns in order to add those up in logarithmic time. And so you'll have n cubed over 2 processors each. And for summing them up, or across the whole thing. So we've got processors in the interior, and then pairs. Then it uses pairs of elements to do the addition and the scan, and in the reduction. So what about the scan primitive? So this is sort of one of the more interesting ones. Well, we could do something like a reduction operation. So remember that the scan operation is doing these reductions, but it's really partial reductions all the way through the array. And we can do it in a bunch of different kind of values. So how are we going to do this in parallel? Well, if we looked at the pseudocode for what this looks like for something like an add scan, it's just running through the output array and adding each of the corresponding elements x sub I onto the previous result in position y sub I minus 1, and then putting the result in y sub I. So this is a computation that in serial time takes n minus 1 operations, these adds, to do serially. But what about parallel? Well, it looks like an inherently serial algorithm. So the ith iteration of the loop depends completely on the I minus first iteration. So we can't really parallelize this directly as it's written down because of this dependence in it. What we can do is think about adding up, how is it useful if we add up some things in parallel? So for example, if we add up 5, 6, 7, and 8, well, that's going to be useful for computing this last result, the 36 here, even if we don't yet have the sum of 1, 3, 6, and 10. But it'll be useful for that. And similarly, if we have the sum of 1, 3, 6, and 10, we can also do something useful with that. Well, let me first look at what if we used a whole bunch of processors, and we put a set of processors at every one of these positions to do the parallel reduction. You can do it in logarithmic time. So the first one only needs 1 processor. The second one, well, only needs 1 processor because it's adding up 2 things. And then you start to get up to log n processors when you get to the end of the set, but you're doing an awful lot of work inside of this, because you're redundantly adding up all of the, say 1, 2, 3, 4, 5, 6, and then you're for both the position 7 and the position 8 and the position 6 if you're doing an inclusive one. So going back to our better idea here, we're going to look at, well, what if we add up these 2 pieces of the array, and what can we do with those things? So, and suppose also kind of recursively that we added up 1 and 2, and then added up 3 and 4 pairwise. Well, the sum of 1 and 2 is going to be useful to us for adding for the 6 and for computing the 10, whereas and the other partial things are going to be useful for the results to their right. So here's the idea of the first kind of useful algorithm for the sum scan, which is this also called parallel prefix. And this is we're going to start with first a pairwise sum. So we're going to just add up the first and second element, the third and fourth element, and so on. And then we're going to do a recursive call essentially to our parallel sum scan algorithm. And that'll also do a prefix sum in parallel, and we'll get the result of that. That's on these values that came out of the first pairwise sum, so the 3, 7, 11. And you can see if we add up, we do a sum scan on those, we get this next array 3, 10, 21, and so on. And by the way, these are arbitrary values here that I happen to have used the numbers 1 through 16, just to make it a little bit easier to see what the sums are as you go along. So if we've got that recursively computed scan, the array scan of this half the size array of each of these pairs of elements, we can then use that to compute the output. And how do we compute the output? Well, you have to look at it a little bit carefully, but we're going to use, the 1 is just going to get passed down, right? Because we're not adding anything to the 1, and that's going to be in the final result. Then we're going to take the 3, for example, that is coming from adding the 1 and the 2 together, and this is going to be passed down to the position down below it. The 3 then that is in the input here up above is also added on to the 3 in order to get a 6. And then the 10 is going to be added to the 5 to get 15 and so on. So you can see that by taking each one of these results and adding something that was in the input to them, then we're going to get these values that are in the output array. And the other outputs then we've already computed from the recursive scan. And so we just pass those values like these, every other one, the 3, the 10, the 21 down into the output array. So what is the cost of this parallel prefix algorithm? So if we looked at how much work it was doing on a single processor, just to figure out what we often want to know what is the efficiency of it from a work standpoint, and the total number of operations is actually 2n. So it is actually doing twice as much work as the original serial algorithm, which was just doing order n work, or n-1 addition operations, to be precise, and this one's going to do 2n-1 operations. On the other hand, in parallel, on an unbounded number of processors, the span is 2 log n. So we've got this this tree. There's the pairwise sum, recursive prefix, and then the pairwise sum again. So it's good parallelism, and it's actually not a bad algorithm, but it does come with twice as much work. So another question that came up historically in parallel algorithms is, can you do an even better job? And this is the algorithm, by the way, that's often used on GPUs, is something that is a non-recursive exclusive scan algorithm, and it will also be an in-place algorithm. This is an algorithm due to Guy Blelek. So I'm just going to kind of walk through it to see, so you can see what happens. The code for it is not too bad, but you do have to just get your indices all straight to figure out what you're going to add up. So you start by doing a pairwise sum. And although I'm going to show you each successive array, you can actually overwrite the array in this case, which is one of the really nice properties of this. And so I'm going to keep track of my distance, the distance between the things that I'm adding together. And I start out with a distance of 1, which is, and this is the exponent, so 2 to the d, and is going to give me a distance of 1. So some of the elements, the even ones just get passed, don't get overwritten, and the odd ones get overwritten by this sum. And then when d is equal to 1, we're going to be jumping by 2, so 2 to the 1, and then we've got this sum that we're adding up this pair of numbers, as you can see from the arrows. And similarly, when d is equal to 2, we're going to jump by 4 and add up these 2 elements that are at the top there. So this is called the upsweep of the algorithm, and then we'll do the downsweep of the algorithm. And notice that at each step we're not doing an add on every one of the positions. So this is going to have a better work efficiency for that reason. So now I've just copied this so that we can see what it looks like sort of going down. We think of these as trees, and this tree is going to go in the other direction. So we'll start with, first of all, we have to do one special operation, which is we have to zero out the last element of this, which might seem kind of silly because we've got the final answer here that we want, but we're going to need that for other parts of the computation. So we zero out the last element. We then use d equals 2. So we look at these kind of long distance things 4 apart, and we swap the 0 into this position with the x03. And that's the sum of things from 0 to 3. And then we do, for d is equal to 1, we're going to swap things that are 2 apart. And then for d is equal to 0, we swap things that are 1 apart. And conveniently now we've ended up with the things that are the partial sums here in the final output array. So any questions about that? So this was, I should point out, this was an exclusive sum scan, but as I said before, if you want the inclusive one, you can just add the input array to it at the end, and that'll give you the inclusive value. And this is both work efficient, it's doing n adds, and it's also space efficient because you can update in place. And that's probably even more important than the add, than the work efficiency of this algorithm. And that's why it does get used in practice on machines like GPUs. Now, that's really all the primitives and the cost of those primitives on our parallel machine, on our ideal machine model. At the end, I'm going to talk a little bit about real hardware and how these kinds of algorithms get mapped onto real hardware. But first, I want to talk about some applications that use data parallelism and use it in a non-trivial way. So basically, this is going to be algorithms that are using scans in some interesting way. And one of the reasons to do this is because it helps us think about problems when you look at them and it looks like they're serial. It doesn't seem like they have obvious parallelism, and then you'll see what comes out, that you can actually still parallelize these kinds of algorithms. So here's just a list of a whole bunch of things that have been done with scan operations. I'm going to go through and give you some ideas of a few of these. It'll depend a little bit on how much time we have. But I think we have plenty of time to go through a bunch of these interesting examples. These are some of the citations, the names in here are particularly work done by people at Berkeley, and looking at some of these different kinds of parallel algorithms. And there's, I guess, an even longer list. Okay, so let's start with a really trivial sort of problem, and that is stream compression. So in stream compression, what we have is an array of values, and we want to throw out some of the values. So it's a very simple kind of compression idea. We're just going to make it smaller by throwing some things away. And so we're going to have an array of flags, and this array of flags, excuse me, is written as just going to be ones and zeros. And we're going to keep all of the things in the values array that are at a position, a blue position is shown here, which have a 1 in the flags array. So you can see the result there. And so the step is going to be to start by computing an exclusive add scan of the flags array. So if you sum up, you do the scan of this flags array, what you get here is this array that has 0, 1, 1, 2, 3, 4, 3, etc. And we're going to use that to actually index into the result array, but we're also going to use a mask. So we're going to scatter the values into the result array. We're going to avoid the fact that we would have collisions between, say, all these different values that get a 3 by masking things by the value that we had in the original flags array. So we only end up having 1 right going into each position. And so we end up with this compressed version of the array. So let's see, we can also do something like remove. We can go through an array and remove a bunch of elements that match a particular pattern. In this case, let's say that we want to go through and remove all the elements that are not divisible by x. So we have a little find function, which I'm going to use at each element. So this is an element-wise function I'll apply across the array, which is find x given y, and it's going to return a 1 if it's divisible and a 0 if not. And so if we've got this input array values and we have a flags array, we can then compute a flags array, which tells us whether it's divisible by some particular value, let's say 3. So if we pass in find 3, and that'll filter out, give us a flags array that is all the elements, the positions that are divisible by 3, and we use that to then remove the elements. We can compress them using this solution from the previous slide. Okay, so the next thing we'll look at is sorting. And sorting, there are a few different algorithms. Of course, there's many different algorithms that you can use for sorting. One of the ones that comes up in this data parallel setting, and therefore it gets used on GPUs and other kinds of data parallel hardware, is a radix sort. And I think that hopefully you may be familiar with this, but in case you're not, the idea is that we're going to sort the array one bit at a time. So we're going to sort it over and over again based on a different bit. So, and if we think of the zeros, we're going to put the zeros as the smaller values on the left and the ones on the right. We're going to use what's called a stable sorting algorithm, meaning that we'll never rearrange anything that had been arranged from where it was in the input to that step. So it's important that we keep it in order, except when it has to be rearranged in order to fix the zeros on the left and ones on the right. And we're going to start with the least significant bit and then move to the most significant bit. And so if you can think about what this is going to do, it's going to put like all of the even things on the left and all the odd things on the right. And then on the next step, you're going to really sort things based on what is larger based on the next bit, but it's going to preserve the fact that the things with a 0 are going to become before the things with the 1 as the last bit because of the stable sorting property. So here's a little bit about how it works in this particular input array. So we're going to sort on the bit 0, and sorting on bit 0 means that we're going to put, as I said, all the 0 things on the left. And so in this particular array, we have 4 even values and 4 odd values. And of course, we actually just have the numbers 0 through 7 actually in those 8 positions. So when we sort this, we will do a stable sort even in this step. So the 4, the 2, the 6, and the 0 remain in the order that they were in the original array, but we've shifted them all to the bottom, and we shift the orange things, the odd ones, to the top, but we leave them in order. So next we'll stably sort it on the next bit, so on the ones position. So now we end up with these, the things that are smaller is based on things that in the second position have a 0 there end up on the left, and the ones that have do not end up on the right. And similarly, then we can do the next thing, do the same thing on the next bit, and we'll stably sort on this array. And so in order to now do this, we're going to be looking at the things that are larger than 4 or 4 or larger, and the things that are so they have a ones bit in that position for the 4. And the others, which are smaller, and that ends up giving us, as you can see now, just by shifting all the orange things, sorry, I think I might have miscolored this last array, but shifting the orange things to the right and the blue things to the left, we'll end up with all of the, we'll end up with this array being sorted. Okay, so that's just radix sort, nothing about parallelism here. It's just, it tends to be an algorithm that is actually convenient for parallelization. And that's because this idea of sorting one bit at a time is something that we're going to be able to do efficiently on our data parallel machine. So let's look at just what happens, and it actually is a non-trivial number of steps in order to sort based on a particular bit of this input array. And so as written here, we're just going to look at the last bit. So we're going to compute, but we could use this same pseudo code for other bits that we did before, but this whole slide is now really just sorting on one bit, the last bit. So we compute an array called the odds, which is putting a 1 anytime the input contained an odd value. So looking at the last bit in the input, did it have a 0 or a 1? If it had a 0, you put a 0 in the odds array, and if it had a 1, you put a 1. And the important thing now to think about is that something you can do in parallel? And the answer is yes, you can do this in parallel in constant time, right? You can compute these odds. And then the evens will just be the complement of those, which we can also compute just by looking either at the last bit in the input or by looking at just by complementing the odds array. So we now have 2 other temporary arrays. We've made up the odds array and the evens array. We'll now make up another array called the evens position, which is the exclusive sum scan of the evens array. So we take this evens array and we do the sum scan on it, which gives us the 1, 1, 2, 3, etc. It's exclusive, so there's a 0 in the front. And because it's also exclusive, there is the sum of all of the elements in it, which is 4. And we're going to just put that off to the right. It is coming out of the fact that we're doing an exclusive scan that produces that 4 value as the sum of everything that's in the array. And let's see, the next question is about, let's see, so there's a question in, and one of them will go back to the I'm going to let somebody else maybe answer that in the chat about the in-place sorting algorithm. I think there was actually an addition in the downsweep as well. But the question is, how do we deal with non-contiguous memory accesses when using all of these ideas? We're going to basically use scatter and gather operations. So you're going to use things like indexed arrays that are going to be reading and writing from a contiguous chunk of memory, but into but not necessarily in order. And I will give you an example in a few minutes about a pointer-based data structure, but it'll still be it'll still look like an array. So we're still going to have some aspects of that, because we have to have the ability to sort of place the processors all throughout these data structures. And so let's look at the evens array. And the next array that we compute is something called the total number of evens, which is just the last value that came out of the sum scan of the evens array, and that is now just broadcast across this total evens array. We then just make up, and this is a constant value that we often use in a data parallel algorithm, and in that, which is just the indices from 0 up to n. So this is just a constant array that we can make up based on, say, your thread ID, for example. And then we're going to compute something which is the indexed, which is going to, the odd positions, which has this little formula that's looking at the total number of evens. And what is the idea here? We want to move all the odds to the right in the array, right? So we're gonna figure out what position each one of these odd values in the input array goes to, and it's going to go to a position that starts at position 4, because that's where the beginning of all the odds starts, because there's 4 things to the left. And so we start with 4 plus whatever index was in the index array. And then we have to subtract from that the evens position, and in order to give us, figure out how much space there was, and that'll give us the position for the odds. And then we compute the pos array, which is doing, it looks like a conditional here, but it can be done with mask operations, I think, in a pretty trivial way, by just saying, well, look at the evens array, use that as a mask, and then we'll write into the pos array something that's either the evens pod or the odds pos. So doing 2 different assignments, both under the opposite mask. And then we'll scatter the input using this positions array, the pos array, as the index, and that'll give us the set of values in which the odds are on the left, the evens on the right, and did I do that wrong? Let's see. Oh, sorry. This is the using this position as the index, and so here's the actual scatter operation. Result of that, we've got the evens on the left and the odds on the right here. And then, to actually do the sorting, this is only sorted based on 1 bit, so it may seem like a lot of steps, but all of these are actually efficient steps inside of this this one sorting step based on the 1-bit sorting algorithm. Any questions about that? Okay, so the next example is what's called list ranking, and it's really just the easiest thing that we can talk about on a linked list data structure. Now, the way to think about a linked list data structure, though, in this case, is it's not sitting, each one of these nodes in the list is not sitting at an arbitrary place in memory, but we have the ability to sort of put a processor at each one of those places, so we can find all the elements. You might think of this as being an array in memory, in which each array element has 2 elements, and one of them is an index of the next thing in the list. And so this list, although it's shown here in this nice sort of contiguous order, could be scrambled all over in memory in terms of where it's laid out, that the first element may be sitting over near the end of the list, and the second one somewhere in the middle, and so on. So we can have the list arbitrarily linked, and the list ranking problem is given a list of n nodes, find the distance from the distance from that node to the end of the list, and that's going to give us the rank. And so and that's just the definition of what the rank of the node in the list is. So this little d function is defining the distance. The distance is 0 if the next pointer is null. Otherwise, it's 1 plus the distance of the next element in the list. So it looks like a fairly serial thing to do. Again, probably pretty hard to parallelize, but when we put a processor at every one of these nodes in the linked list, we can actually run something that is a parallel algorithm here. So what we'll do is pointer doubling. And so in pointer doubling, we take the pointer in this array and we're going to make it point to its next pointer. So we take something that points to next and then add 2 to it, or add 1 to it, because we're doubling it actually. So we're doubling the distance to the next thing. Here at the end of the list, you can see something special is happening, and this is going to be under, say, a mask, which is saying that if our next pointer is null, or in this case, our next pointer is null, then we don't add 1 to the rank, the value that's sitting at that pointer. And in the next iteration, we're going to be jumping now by 4. And so we've got a distance of 4 to the end, and you can see the 3 has been filled in because we are, for something that's near the end. And similarly, then we get the 8 filled in here, and eventually we'll get everything, all the values of the ranks filled in. And I just want to remind you what I said earlier, that it may look like this is only working because things are sort of laid out nicely in memory in this order based on the order of the linked list, but the algorithm will work even if these pointers are pointing all over the place. It just would be very hard to draw on the screen. So the next example look at is solving a recurrence for the Fibonacci number. And this is, but is actually a general technique that can be used for other recurrences. And it turns the problem into a little 2x2 matrix multiply problem. And so if we write down the Fibonacci function says that Fibonacci, the n plus first Fibonacci number is the nth Fibonacci plus the n minus first Fibonacci. And we can write this in this little matrix form, which says that fn plus 1 and fn are equal to this little 2x2 matrix times fn and fn minus 1. And so we can compute all of the fn's by doing a matrix multiply prefix on this, because you can sort of keep doing substitution, and you're going to get this whole, a string of 1, 1, 1, 0 2x2 matrices. And so we can multiply them together using matrix multiply parallel, using parallel prefix as with matrix, the 2x2 matrix multiply as the operator in the parallel prefix, and then look at the upper left entry, and that'll give you the nth Fibonacci number. Now, that may seem like kind of a silly way to compute Fibonacci, given that there's a closed form formula for it. But as I said, it's a useful way of thinking about other recurrences. And in particular, it can be used to add up n-bit numbers in logarithmic time, where we're thinking of our n-bit numbers now as an array of bits. So A and B are array of bits here written out as, and we're going to write them with the most significant bit first, not surprisingly down. And so it's written out in this notation. And then we're going to compute the sum, which is A plus B. And that's also going to be an array of bits that goes from n down to 0 because of the possibility of carrying forward. So there's a question about what do I mean by putting a processor at every node? I think that means back in the linked list example. So a processor at every node means that in parallel, we can, for example, do iteration 1 in constant time. That is, if we've got, so imagine that this array, that this linked list is actually stored as an array of 2 values. It's rank, which is what you're going to be filling in, the result, and the pointer, the index of the next thing. So that's the easiest way for me to think about how I would, for example, run this on a GPU, which is it's a linked list, but the next pointers are actually integer indices into the next position. They don't have to be, but that's the way that I can sort of think about, now I've got an array that's storing this linked list in an arbitrary order, and I'm going to put a processor at every one of those positions, and it will be responsible for looking at its next pointer and checking to see whether its next pointer is null, and if not, then storing in its own position its the pointer of its successor. And that is how you get the doubling to work. So the question is, can we parallelize the process of putting a processor at every node? As I've described it, yes, right? If I've got an array of, if I've got these things laid out in an array, then I can just sort of like on a GPU or something, I can hand that whole array to as a set of threads, and they can all operate in order. If you're wondering, and this is where, you know, if I've got this linked list laid out all over memory, I do have to sort of figure out where all of those nodes are in order to put a processor, in order to give that node to a processor. So I'm assuming here that I've got the ability to sort of pick up all of the nodes at once. I'm just trying to figure out how they're linked together. I'm not sure if that's answered the question, but putting a processor, okay, well, let's see. Okay, so let's look at how we use the same idea in computing and adding n-bit numbers, this sort of Fibonacci recurrence idea. And so if we are looking at how, from a bit arithmetic standpoint, we're doing integer arithmetic, we're trying to figure out how to compute the sum, which is this array S, which may have one extra bit in it because of the carry. And we're going to also compute a carry bit array, which is going to be indexed in a kind of funny way from n-1 down to -1. And that'll just make some of the index arithmetic a little bit easier. So the formula for the carry bit is that the carry bit, the -1st carry bit is 0 because you can't, there's nothing over there to have carried into. And the and then for and this is kind of giving you an idea of why you need that extra position so you can make the rest of the recurrence work out without a special case in it. And so for the other positions, the ith carry bit is going to be, you can see from the second line here, is an XOR of the A and the B bit and the C minus first bit, or the A and the B bit. Now I'm not going to go through the logic of this, but maybe it's easier to do the sum one because it doesn't have quite so many terms in it. But if you're looking at what the output is going to be, and you need to look at three things. You need to look at the carry bit that's coming from your right, so the C minus first carry bit, and then you're looking at the bits at position I in both A and B. And it basically, if one or three of those are ones, you're going to end up with a 1 in this position. You're going to end up with an odd result, and depending on whether it was 1 or 3, your carry bit is also is going to be 1 that gets passed along. But the point is that the sum bit is just depending on whether you've got 1 or 3, and if it's 0 or 2, then it's going to be a 0 as the output. Okay. And this other formula for the carry bit then tells you whether or not that carry bit is going to end up being a 1 or a 0. Okay, so here's a little example. I don't think I'll read through this, but it's on the slide, so you can kind of work through it if you want to see that it really is going to be, we've got these inputs A and B, we've got the carry bit, which has an extra thing over here, and we've got the sum, which is the output. And when you add these bits together, if you check the arithmetic for each one of these are the logic for each one of these ones and zeros in here, it will give you this result. And so that's how we're going to do n-bit arithmetic. And now the sum calculation that we had here looks like something we can do in constant time, right? There's just two XOR operations with three values here, the A, B, and the C minus 1. So that's a step that can be done in parallel in constant time across all of the bits. The carry bit has this recurrence in it, so we've got a little bit more of a problem. And so it turns out that we're going to use this same idea of doing it in logarithmic time by writing this down as a recurrence. So how we can write it out in a little bit more detail, and this is what the hardware will actually do by having a propagate bit and a generate bit, and the propagate bit PI and the generate bit GI, that are breaking down sort of how I'm going to calculate then the carry bit. And we can now write down the recurrence of CI as this formula. It's the propagate and the carry bit, or the generate bit. If that formula is 1, then we're going to end up with 1. Otherwise, we're going to end up with a 0. And so we can take this formula, write it in this matrix notation with the pi and the gi, these temporary vectors that I've made up here, and then write down this recurrence that has ci minus 1 times the propagate and generate bit. And so I'll just write this little this matrix, the little 2x2 matrix, as m sub I, and that is going to look a lot like that Fibonacci example that we had before. And so we can now do these with 2x2 parallel prefix. And these are 2x2 matrix multiplication, which is associative. So this will work just fine. And we're not doing any floating point at this point. We're just doing Boolean arithmetic. And this is actually used in computers in terms of how they do arithmetic. And in fact, it was used even in the Babbage computer. So this idea of efficient way of adding up numbers was done using, even in this ancient computer, now this adding machine. Okay, let me see how I'm doing. I think we've got plenty of time. I will talk a little bit about lexical analysis. Now, this may be something, if you've taken a compiler course like 164 or something else, or anything in which you've been parsing some kind of program text and trying to, or even natural language text and trying to turn it into tokens. That's what we're doing here, is what's called lexical analysis. It's not fully the parsing step, but lexical analysis says I've got, say, a program written in some language, and I'm trying to, and the compiler that's analyzing it is taking the strings, that string of the program text, and turning it into things like these tokens. Like in this little bit of code here in the rightmost box, we've got if x is less than or equal to n, then print hello world. And so the if, the hello world, the print, each one of those is a separate token. So that's all I'm trying to do right now at this particular stage, is figure out what are the tokens. And they're going to be separated, for example, by white spaces, or there's certain rules that say if I've got the beginning of a quote and I hit a white space, then it's still in the middle of the string. So the hello and the world are part of the same token, even though there's a space between the two of them. And the way this is done in compilers is building a finite state machine. And I've written out a little, this is a little grammar, and this is an example that's in the Hillis and Steele paper. I'll say a little bit more about them later when we talk about hardware, but this is really sort of the classic paper on data parallel algorithms. And some of the other examples I've talked about are also in that paper. So I highly recommend it if you want to look at the history of parallelism and what things looked like back in the late 80s. So this is, but in this little language here, what do we have? Well, we have identifiers, which are strings of characters. We have strings that are in quotes that might have spaces in them, whereas an identifier doesn't have a string in it. We have operators like plus and minus, times, less than or equals, and so on. There's expressions in quotes and some other things in here, but I'm not going to go into detail. And I haven't written out the entire finite state machine. But the basic idea is if you see, for example, the character I, that means you're in, it looks like you're in an identifier. And as long as you keep seeing characters, the letters A through Z, you're going to continue being an identifier, which is the Z state of the state machine. Whereas if you run into a times operation, you're going to go up into this sort of operator state. And then if you see a less than operation, you're going to go into this special less than state, which is a little different than the other operators, because you can put a less than onto an equal sign and so on. So this is the finite state machine, and you basically, in parsing and doing lexical analysis on the input string, you're just going to work your way, sort of, go around through this state machine to figure out what which ones of these are which kinds of tokens, and break the input text into tokens, and then label each one of them with the type of token that it is. So this finite state machine, actually the complete one, this is an incomplete picture up here on the upper right with the arrows and so on, the little graph. A complete version of that state machine is actually written out down here in this table. And the table is taken from the Hillis and Steele paper, which is why it looks a little bit fuzzy. And the way to read this table is if I'm in a particular state, which is the old state, so that first column. So let's say that I'm in the state Z, and I see another character, which I read off of the right of the top here, A, B through Z, or plus or minus. If I see an A through Z, I'm going to stay in the Z state. So that says that the next state after I'm seeing is from the Z state is a Z state. If I see one of these other characters, I'm going to go into the star state, which is representing the operators. If I'm in a less than or greater than, I'm in one of those kind of quote less than states. I don't, at this point, I don't care whether it's a less than or a greater than. I only care about the fact that a less than or greater than can be attached to an equal. And so I need to know whether it's just one of these, conditionals or comparisons by itself, or something that also has an equal attached to it. And so this table, you start with a state that you're in, and then you look up what state you go into depending on what character you read next. And given that, you can then turn this program text into these tokens. Okay, so that's the way the serial algorithm works. Nothing parallel about that. I guess the one thing that you might want to think about is that we'll think about this as applying the string to a particular state. So for example, if I'm in the state Z, this is the third bulleted point here on the right. So if I'm in the state, this orange Z state, which is the identifier state, and I see the letter Y, then that means that I'm going to stay in the Z state. So I can write that, and if I have a quote and a plus, I'm going to apply that to the Z state. So I can write that as Z followed by Y quote plus. And I can think of that as Z applied to Y, the result of that applied to quote, the result of that applied to plus. And so you can see how it gets evaluated here. And eventually we see that we're in a string type. And so that's how it kind of operates as a, you can think of this as this operator that is taking a state and turning it into another state based on an input string. Okay, so how are we going to parallelize this? So generally finite state machines seem like they're pretty serial things that you just are walking through the state looking at one character at a time. How can you possibly parallelize that? Well, the answer is that you can think of this kind of table and look at the table here that's in white, and you can build for that for every character in the input string its next state based on an assumption of what state it was coming from. So what we're going to do is for the input text here, which is the IFX less than equal n, we're going to build just looking at the I by itself. So this is a completely parallel step. We can build the next state from that. And we can then compose them together using this little plus star operator and do that in logarithmic time, because there actually can be, so it's going to be a state to state mapping based on what that one character is. And I can parallelize this using parallel prefix. So that is the pretty non-obvious way to do something as what seems as serial as parsing and or as lexical analysis. And this idea was used by Ross Bodek and Leo Majowicz in a paper looking at analyzing web pages and parallelizing the parsing and analysis and layout for web pages to this kind of trick. So I think perhaps my last example is looking at inverting a triangular n by n matrix. And in order to see how we're going to do this, we need to know a basic linear algebra fact, which is if I've got a triangular matrix that I can write of this form, A0CB, that its inverse is equal to A inverse, B inverse, and then this expression B inverse or minus B inverse times C times A times A inverse. So you have to just know that basic linear algebra fact. And now we can use that to define a recursive function. And the recursive function, which we're calling this tri-inverse or tri-inv of this triangular matrix T. And we're going to just assume it's a power of 2 in each dimension, just so it's square, and a power of 2 for simplicity. Well, it's a triangular matrix. But anyway, so if T is a 1 by 1, then we'll just return 1 over T. And otherwise, we'll think of T as containing, these temporary variables that we're making up in the code, A, B, and C. And we can do that by dividing up the matrix. And then in parallel, we're going to compute the inverse of A and the inverse of B, both of which are also triangular matrices. And so that can be done, with a recursive call here. And we can do those 2 steps in parallel, by the way. And so implicitly, this is going to unfold as a tree. And then we are going to compute this value nu C, which is a matrix, by taking the inverse of B. So this can't be done in parallel, or at least as written, this is done serially after we've computed an inverse of A and inverse of B. And we take minus b, A inverse of b times c times a, and this is going to be logarithmic time because these are matrix multiplies, and well, and they're n/2 size matrix multiplies. And once we've got nu c, then we're going to just return the matrix inverse A, 0, nu c, and inverse B. Okay. And so what is the time to perform this, recursive function? Well, it's going to be the time to solve in parallel. So we're not going to multiply it times 2, the problem that's half the size, the tri-inv of n/2, plus something that has logarithmic cost in here. And if you do a change of variables to figure out what the overall cost of this is, it's a log squared n computation. Okay, I guess I do have a couple of other examples, and the last ones here are now looking at segmented scans, or last one. I think I just have one example here. A segmented scan is just like a scan, except that you put sort of blocks or barriers, whatever. I don't want to use the word barrier because that means something in parallel, but something guards in between these various points that say that when I do the scan, I'm going to stop the scan at a particular point and start over again at the next array element. So we're going to take as input some value array that we want to do our segmented scan, some associative operator that we're going to do the scan on, and then a flag array that can be stored in various formats. I've shown it here with Booleans, false and true. It could be ones and zeros. It depends on your language, but all of them are roughly equivalent, or maybe just a 1 at each one of the positions where the flags change state. So if we do an inclusive sum scan on this array of the numbers 1 through 8, and we have a flags array, which has it does have a 1 at each one of the positions where the state changes, where the false and trues change over here on the right. Then the result that we get is, for the inclusive scan, is 1 and 1 plus 2, which gives us the 3. Then for the next position, because it's just to the right of one of the flags, we're going to get a 3, and then 3 plus 4 to get 7, and then 3 plus 4 plus 5 to get 12, and so on. Whoops. So the segmented scan is also useful for things, and I'm not sure if I just do something for a second here. No, I don't think I can do that. Okay, so let me go back to full screen mode. So I can use this for sparse matrix vector multiply and these segmented scans. And let me just look ahead to make sure I didn't put it in there. I think it's in the online version of the slides to see what we're doing. We can use this to do a dot product on an array, on a matrix, where each one of these segments is going to be one separate row that we're doing a dot product on. And so we can treat it as one big parallel operation, even though each row is really doing its own separate dot product. And in a sparse matrix, which Jim talked about a little bit last week, you have different lengths for each one of the rows. And so these segmented scans are useful because you can sort of pack all the rows together, do one big segmented scan. And by the way, the segmented scan can also be parallelized in logarithmic time. It's a little bit trickier algorithm to make sure you keep the segments all lined up and so on, but you can do that, and that will it will give you the result for the sparse matrix vector multiplier, where you're doing these dot products. Of course, in a sparse matrix vector multiply, you also have to do an index load of the source vector, because you're going to have an index here that says where logically each one of these values lives in the sparse matrix. So we'll talk about sparse matrix vector multiply in a little bit more detail in a few weeks, and I'll go over it then. And in that case, you can we'll talk a little bit more about what this kind of algorithm looks like. But I wanted to make sure you saw the segmented scan, because it is important in a lot of different all of these data parallel algorithms. I think I'm going to let Jim answer or somebody answer the Schur's complement question in the parallel inverse operations. And he's thought more about some of the other linear algebra. He is going to be giving a lecture on dense linear algebra, and we'll talk about dense linear algebra on GPUs as well as other parallel hardware. So that may come up there. Okay, so this lecture today has been all pretty abstract. Sorry, there's a little delay in here. Pretty abstract in terms of these algorithms just running on our abstract parallel machine. And the next thing I want to do, if I can get it to move forward, whoops, is to talk about real hardware. And so I'm going to start with a little history of parallel hardware. And this is the connection machine, which was a machine designed by Danny Hillis, actually when he was a graduate student working with Marvin Minsky at MIT, who is an AI researcher. So this was actually a machine designed for AI, and it was inspired by their ideas of how the brain worked and how they were going to use this for artificial intelligence in a time when AI meant maybe something a little bit narrower or maybe more general than it does today. We're not really referring to deep learning algorithms. I just want to point that out. We're really talking about other kinds of planning algorithms and so on that they were looking at in AI at the time, back in the late 80s. And this was, as I said, it was designed by Danny Hillis when he was a PhD student. He then started a company with Cheryl Handler called Thinking Machines Corporation, and they designed this machine called the Connection Machine 1, the CM1. So the CM1 was a really interesting piece of hardware in that it had only 1-bit processors. So again, think about this as being something that they were thinking of as something that was kind of capture the neural activity of the brain, and you just had these 1-bit processors with 4 kilobytes of memory for each, but they had 64K of these 1-bit processors. And they were connected together in what's called an n-cube network. And I think next time we'll say a little bit more about next week. I may talk a little bit more about that. I don't remember if Jim mentioned the n-cube sort of network ideas, but these are these higher dimensional cubes. This was actually I've seen both 12 and 20 dimensional Boolean hypercube network, and it was actually designed by Feynman, who was working with them over the summers, and it was based on ideas he had used in the Manhattan Project at Los Alamos for computing logarithms. Sorry. And so they decided to use this idea to build this machine, and it was called the connection machine because, according to one of the quotes on the web, that because communication is more important than the processors, and so the machine was really named after the connection network of the machine. Now, the second version of this machine, they realized not everybody wanted to do work just on 1-bit values and 1-bit arithmetic. And so in order to do floating point arithmetic, they added a 32-bit floating point for every 32 1-bit processors. So you think of that as its own little, floating point accelerator attached to some of these 1-bit processors. And this was then became a machine that people used for other scientific computing. In fact, I think Feynman realized that he could use it for quantum chromodynamics calculations. Still one of the things that people will always try to use the high performance machines at the supercomputer centers for. And so that was kind of the history of that machine. These machines were programmed originally. They were at MIT. Danny was at MIT. They were using Lisp a lot especially in the AI research group. And so this was a language called Star Lisp. And think of it as sort of, if you're familiar with Lisp, a language based on all these parentheses and really kind of designed for string manipulation and other kind of lots of recursive functions and things like that, that it was, so Lisp processing. It was a data parallel version of that called Star Lisp. And then there was a data parallel version of C called C star. And that was really what was used for the connection machine 1 and 2. Now, RISC processors, if you remember back to my top 500 graphs from a few weeks ago, the microprocessors, RISC microprocessors were really improving very rapidly in this time frame. And so this was specialized hardware built just for either AI and then kind of broadened to science, but you had this huge community and market for these RISC processors that was growing. And so the Connection Machine 5, which was actually the first big parallel computer that we had here, Jim and I were responsible for buying that along with David Culler and I think maybe Tom Anderson and a couple of other people at the time when we'd just gotten to Berkeley. And so that was a RISC, also this network of processors, but they were RISC processors and with attached vector units. So that brings up the idea of vectors. And so this, unfortunately, I have to say, I really love the connection machine. And I think this paper, as I said, by Hillis and Steele, Guy Steele, who worked on some of those algorithms and some of the compiler and language work there, is really a beautiful piece of parallel computing history. But it was sort of overtaken by, what was happening with Moore's law, but generally Dennard scaling and so on, and just processors getting faster. And they couldn't have a special design team just building processors for this purpose. So what about vector processors? If you've got a data, so hopefully a data parallel computation on this thing, which had its one control processor. I mean, this really is sort of the implementation of our abstract machine model, other than the fact that it does have some cost for communication and it does have a finite number of processors, but it's pretty straightforward to map these onto, onto the CM1 and the CM2 sorts of SIMD designs. If you've got a vector processor, and we've seen this in the SIMD instructions, then we've got these vector registers that are a certain width, and they can hold a certain number of values, let's say 32 values, and then you're in parallel adding, say, 2 vector registers together. And so these data parallel algorithms also map pretty well onto those vector instructions. And the vectors, by the way, and one of the differences between old style vector supercomputers. So remember Cray and his, I'd rather have 2 oxen than a herd of chickens or whatever, a field full of chickens. Well, he was building these big vector supercomputers. They had pretty wide vectors, and they virtualized, though, exactly how much parallelism there was. So the number of lanes, which we also talk about in GPUs, is sort of the physical amount of parallelism that's actually going to execute in a single cycle, and the logical width of those vector units, which is the width of the vector lane, the vector register, is it's not just logical, it's a physical length of the vector register, going to be longer. And the nice thing about that is if you write some code or even a compiler that generates a code for a certain width vector unit, and then a new generation of vector processor comes out, the code is still going to run on that. And so we looked at this in this architecture, the vector architecture, in the VIRAM project at Berkeley. Let me see if this is going. Oh, this is just saying that we're virtualizing, yes, the add operation. If we only had 2 lanes, then we would start by just doing 2 additions at once, and then 2 more, and so on. And so that is, but it's kind of hiding from the software exactly how fast that's going to go and how much parallelism is inside the hardware. We designed, so Dave Patterson led this project, but I worked with him on the compiler and some of the algorithms for the VIRAM project. And this was a vector processor and memory project. So it had the memory, the DRAM actually on the processor chip. The chip was fabricated. Krista Asanovich was a grad student at the time, and he was finishing his PhD thesis. But he gave some advice on this. He was really looking at AI algorithms. By the way, there's a great YouTube video of him also giving a lecture on the history of AI hardware, which includes these kinds of older vector processors and things. And this is what it looked like. The other thing you need in order to, so it should be pretty clear how you map things like unary or binary, add operations or whatever onto these vector units. But if you have something like a reduction, well, it's fine as long as the array that you're reducing is, at least twice as long as your register. You just keep sort of doing recursive, the opposite of doubling, so having them, just keep adding them together. Once you get down to an array that fits inside the register, and the register in this case is, say, 32 elements wide, then there have to be special in-register permutation instructions in order to finish this up. And there's a bunch of work that was done on what those look like. And that's something that the SIMD extensions on uniprocessors or on single cores are getting better and better at over time. But when the SIMD instructions first came out, they didn't have very many flexible in-register permutation instructions. Mapping onto GPUs, hopefully that also is pretty obvious in terms of how it happens. We do think of it as being a thread, that you're writing the code for each one of these threads, but just the picture even here of our GPU with a single SM having its one fetch and decode unit is really like that abstract machine model. The one thing you have to do when you're writing GPU code is you've got to break things into your N threads and your M blocks. So you've got two-way parallelism, so your data parallel algorithms are going to have to be mapped into that. And as I mentioned last time, they use different types of communication and synchronization between the 2 different levels. So, you know, bottom line on these GPUs and kind of these data parallel algorithms, you know, things like branches are still expensive because the hardware really has a certain aspect of data parallelism in it down at the warp or sub warp level, and which is the kind of the hardware notion of parallelism. And the number of threads in a block is that virtualized kind of larger set of things that we kind of like a vector register that we don't necessarily have to worry, unless we're really tuning it very precisely for the best performance, exactly how much parallelism is happening at a single step. And we may need to do things in order to get things lined up with, say, your register size, such as padding. You are often going to write code with a guard in it. And that was one thing. There is a correction in the online slides from last time to make sure that the code works correctly for one of the algorithms, to make sure that you're not writing off the end of your array. And so you'll often have these kinds of guards, and if you're which is going to turn into a mask. But if you've got a large array and you're just sort of masking off the last bit of it, power of 2, for example, or non-power of 2 elements that don't exist in the array, then that shouldn't be too bad. Non-contiguous memory is supported. I think this is somewhat related to the question that came up in the chat and in the GPUs and in these data parallel models, but they are going to have higher costs still. And you want enough parallelism to keep all the ALUs busy and to hide the latency if you're going to be having long latency operations, such as memory operations in your inner loop. But there is also some overhead to all of that parallelism, such as the memory footprint, which can overwhelm your GPU processor that has a fixed amount of memory and your scheduling. So, and there's my, let's see. And so mapping, I wanted to just say something, sorry, about mapping onto coarser grained processors, which I'll do quickly here. We have n-way parallelism in our data parallel model, so our arbitrary number of processors for our array of size n. But if we're running it on SMP, or as Aiden will talk about next time on massively parallel processors, MPPs, we have to worry about breaking that into chunks and running each chunk on a processor. And so that gives us cost that looks like, for these unary and binary operations, a perfect P speed up, because it'll run in time n over P. And you do have to worry about the fact that if things are not completely aligned in memory, there is a cost in a non-ideal machine to the communication or false sharing with the cache line moving back and forth around the shared memory multiprocessor. And reductions in broadcasts are also going to speed up, not quite as perfectly, but you're going to do a lot of the work locally. So do n over P work locally, or do each of your n over P operations locally. And that gives you your n over P perfect speed up for P processors. But then there is a log P factor after that to do the tree-based reduction across the processors. But normally P is going to be much smaller than n, so you're going to get almost a factor of P speed up. And the same thing, I won't go through this, but the same thing is true if you map the scan onto kind of big, hefty processors, whether it's a shared memory multiprocessor or a distributed memory multiprocessor. And this slide is just saying that what's really important is the fact that if you've got a very large, if n is much larger than P, that you're really getting this factor of factor of P speed up. It's not really the log P steps that matter in the end. And so with that, I will wrap up, which is just that this is, these data parallel algorithms are really nice. And boy, if we could all program in star Lisp, and it would just, for those of us who like Lisp, or maybe C star or something like that, it was a really elegant way of programming, because it's really sort of lockstep, just serial code that has very wide, data parallel operations in each step. So it makes debugging a lot easier, because you don't have the same kind of non-determinism, and it's much easier to reason about that kind of data parallel code. And then the cost model gives us this nice way of thinking about an arbitrary parallel machine. In practice, the compiler or something had to map it onto the fixed amount of parallelism, and that's really what killed data parallel languages, is the difficulty of this mapping problem onto real hardware. And there's a reference to the classic paper that I've referred to a couple of times, as well as the link to the YouTube video. I'll also point to Guy Blelick's work on the Nestle language, which is a nested data parallel language, and a paper he wrote, still, I guess, a while ago now, but on Nestle Revisited. But there's a lot of beautiful algorithms work in those papers as well. And with that, I will stop. And I think since we're out of time, we'll go ahead and hopefully people have answered whatever questions have come up in the chat. So thanks very much, and we'll see you next time.